All right, everybody. The last part of our notes here from 7.1, a very long section, is yet another variation. This will be variation number 3 here on the exponential growth function that we've talked about in a couple of different incarnations early on. And this one, I want to remind you, it's really the same formula we've seen twice before, but it's kind of tailored now for a particular type of problem, and that would be compound interest. These are going to be money problems where we are either saving money and earning interest from a financial institution for that, which is a good thing, or where we're borrowing money from a bank or a credit card company and having to pay them interest. That's a bad thing. One thing I would like to see here, and I'm going to add this here, there's a word that I really feel ought to be added in front of compounded interest, and that would be the word incremental. Incremental, let's see if I can spell that right, and actually it should probably be an adverb, incrementally compounded interest. I do that to draw a distinction between a different type of interest we're going to learn about in the next section, which is going to be something called continuously compounded interest, and that's going to be something different. So here's the formula, guys. It looks messy. A is equal to P times 1 plus R over N, all raised to the NT power. What? All right, let's talk about what every one of those variables means. In the previous two versions of this formula, the left side has just been Y. Here it's called A, but it still represents the same thing, guys. The current, or more likely the final amount of whatever it is that's growing over time. And the word balance is what we use in the financial world to talk about the amount of money that's in an account at a particular time. So even though it's A, it still represents the same thing on that left-hand side. Equals, here we go, P. Now, this is confusing because in the previous two versions, this number right here was a lowercase a. Now we have a capital A over here, so I would get why you would be confused about that. So it's something new. We use capital P because it stands for the word principal. And this is not the principal of your school, everybody. When we're talking about money, the principal is the amount of money that originally was present at the start of this loan or this account or whatever it is that we're dealing with right there. So financially speaking, the principal is the amount of money you began with. So even though it's a new variable and a new word, it still represents the initial amount of whatever it is that we're talking about growing over time. All right, that is the coefficient. And now what comes next is once again the base of the exponent. And just like in the last version of this formula, where we were talking about, what do we do? Websites, I think, that were growing, something like that, you're going to take 1 plus R, except this R now gets divided by N. What does that mean and why do we do it? Well, here we go. The R still stands for the interest rate. Now, we called that the rate of growth in the previous section. That's what interest is. And once again, that interest rate is always going to be given to you as a percentage that you're then going to have to convert into a decimal. But that interest rate now gets divided by N, and this is new. N is the number of times per year that your interest is compounded. So just imagine, this is back in the early 1900s, before there were computers, and there was just some math nerd like me sitting in the back room at a bank, and once a month or once a week or once a year, I take out all the books and I look at all of my clients that I have here. Maybe at that point it was dozens or hundreds. If it was a big bank, maybe thousands. And I sit there and do the math and say, okay, for this month or for this week, this is how much money you have in your account now. So the number of times we do that per year is N. And then that base gets raised to a power here that's just a little bit more complicated than it was before. Previously, that exponent was just a t for time. Now, it's the product of n multiplied by t, where once again, n is still the number of times per year that we're compounding your interest, and t is measured in the number of years. Now, the reason this formula looks much more complicated than what we had before has to do with something that I talked about when we did this problem before, guys. The key here in an exponential growth model is that this unit of time right here and the unit of time used in the rate have to match up with each other. Like, for example, in this problem right here, we were talking about websites growing at 97% per year. And then the question was, how many websites were registered by 1996? So from 1993 to 1996 was a time period here of 3 what? 3 years. And because we were talking years here and years here, we had no problem here at all. We didn't have to worry about units matching up. Unfortunately, in most of the financial problems that we do, those units don't match up on their own. So what this formula is doing right here and right here is it's forcing those time units to match up. I'll explain what that means in a little greater detail as we dive into our first example. So let's take a look at this one, guys. And we're going to start off with the scary thing. We're going to start off with an example of what happens when you're not a saver, but you're a borrower. So you're going to go into Best Buy and you're going to buy yourself a new TV, and it's going to cost $1,300. But you're not going to pay $1,300 in cash for this TV. You're not going to write them a check. You're not going to swipe your debit card. All of those things would be examples of money that you've already made, that you've put into your bank account here, and that you're going to pay for them there right up front. What are we doing instead? We're doing something that sounds like a great deal to a lot of young people, but is really pretty dangerous. We're going to buy it on our credit card. And for those who don't know, when you have a credit card from Discover or American Express or Visa or MasterCard, you're spending money that you don't actually have already. You're essentially agreeing, when you sign up for the credit card, to take out a loan from these companies here. You're going to spend $1,300, but it's not your $1,300 here that Best Buy is getting. It's Discover's $1,300. So why would Discover do that for you? Why would they loan you $1,300? They want to make money off you. So you're agreeing then to pay Discover back the $1,300, but at a significant amount of interest here, a 30% APR. Now, I'll tell you guys right now, a 30% APR is a pretty lousy deal. But when you're a young person just starting off, 18, 19, 20 years old, if you don't have much of an established credit history and therefore not a very good credit score, the only credit card you're going to be able to get is one with a lousy interest rate, like maybe as high as 30%. This is definitely something you're going to want to avoid in the real world, but I'm trying to scare you guys here. So let's take a look at what this looks like. So you're going to borrow $1,300 from Discover at 30% APR, and that interest is going to be compounded monthly. Monthly is the way that most financial institutions actually do things in the world. So right there, let's talk about it. When something is happening monthly, how many times per year is that occurring? Well, 12 months in a year, so that's the end value in this particular problem. So without making any payments, how much are we going to owe Discover for our $1,300 TV after 2 years? That first part is a little bit tricky there. You guys really want to be wary of offers that you might see on commercials, TV, web pop-up ads, something like that. When somebody offers you something with no payments for 2 years, be careful. If they say no payments and no interest for 2 years, that's not a bad deal. You're just deferring then, and it's not really hurting you. If you read the fine print carefully. But if they just say no payments for 2 years, let's see what that actually does for you. All right, guys, we're going to use the formula we just wrote down. A equals P times 1 plus R over N raised to the NT power. So without making any payments, how much will we owe after 2 years? It is a question of what is our final balance. So we don't know what A is, so we just leave that as a variable. But that means we better know the value of everything else. P means principal, the amount of money that we took out on this loan. That was $1,300 that we borrowed from Best Buy. Then in parentheses, let's work on the base of our exponent. 1 plus, and here we go. R is the annual percentage rate. That's what APR stands for, guys. Annual percentage rate of 30%. We have to convert that to a decimal by sliding this decimal 2 places to the left, and that's going to be 0.30. Divided by N, the number of times per year they're calculating our balance here, which is going to be 12. Now let me just stop right there. What they've basically done here, guys, is taken this yearly or annual percentage rate, 30% per year, and by dividing it by 12, what they're doing, you don't have to worry about this, guys, but I think that's 2.5. That's now saying that we're paying 2.5% per month for this interest right here. We've converted here an annual yearly percentage rate into a monthly percentage rate. Now, why is that important? Let me show you what happens next. The exponent now is the product of n times t. N is still going to be 12. So remember, guys, this number and this number are both representing the same variable. Those two numbers should always be identical. So the power is n, and then multiplied by t. The length of time in years for this loan is going to be 2. So what did we just accomplish? Up here, guys, obviously 12 times 2 is 24. And what's the significance of this? We converted our interest rate into a monthly interest rate, and this is the number of months that this loan exists for up until we pay this off here. So a monthly percentage rate here, and now we're in months. So that's where those two units match, just like they did earlier when we were talking about websites growing yearly. Now, the good news is, guys, that's everything in this formula, and the unknown, A, is already isolated. So all we have to do is dump this entire right side into our calculator in one step, and we should be good to go. So let me take a look. You know what, guys? I goofed something up right here. Let me clear everything out. All right, and here we go. So we were borrowing $1,300, and then in parentheses here, it's going to be a 1 plus a fraction now, and our interest rate was 0.30, 30%, divided by 12 times per year, because we're doing everything monthly here. Get out of there, get out of the parentheses, and take that to a power of n times t, 12 times 2. And survey says, take a look, everybody, your $1,300 TV from Best Buy is now going to cost you $23.51 and 34 cents. $23.51 and 34 cents. So I want you guys to realize just what we're saying right here. You go to a store, you find a TV, $1,300, you decide, you know what, that's a fair price, I'm going to buy it. So just imagine you walk up to the cash register and they ring you up and they say, nope, we were just kidding, the TV isn't $1,300, it's actually $2,351, $1,051 more than you thought it was going to cost you. Every single one of us would get mad, and we would walk out of the store at that point without buying the TV. And yet that is exactly what happens in a situation like this, that the things you buy on credit, if you take a long time to pay them off, and especially if they have a very high interest rate, end up costing you twice as much or maybe 3 times as much, could be even more than that, than you initially thought you were going to pay for that. So that's why some people get upset about what they call predatory lending habits right here, that credit card companies tend to prey on lower income individuals here who don't really have any other options. And if people don't realize what they're signing up for, which is very often the case, this is how young people, well, and old people too, get themselves into really bad financial shape by borrowing money because they feel they don't have any other options right there, and paying it off at a really high interest rate. Things end up being significantly more expensive than they really should be. So this is kind of meant to be a cautionary tale to you guys. Now, wait a minute. Let's flip this around now. Let's let interest work in your favor now instead of working against you. And how do you do that? You save money, everybody. So let's take a look at this problem now. You're going to deposit $3,500. Let's say for you guys at your age, you worked all summer at a job and you were careful and you didn't spend your money. This is what you ended up with here. You're going to take that money and you're going to put it into an account that earns 4% annually, meaning 4% per year, and that's going to be compounded quarterly. Now, I'll tell you right now, some of you guys may already be on this track, but if you just have a savings account at your local bank, you're not getting anywhere near 4%. Probably significantly less than 1% is the actual amount. But there are options available to you, and usually the more money you're dealing with, banks are in more of a hurry to get your money and to get your business. They'll start throwing a better interest rate at you right here. Now, compounded quarterly, that's an important word right there. That tells us that the bank is reconfiguring our balance once per quarter. And what does the word quarter mean? It doesn't matter what you're talking about, guys, a football game, a chicken, or a year. If you quarter something, cut it into quarters, there's always going to be 4 pieces right there. So n is equal to 4 anytime we're using the word quarterly. And the question now is, what's your account going to be worth after 5 years? So again, the same formula we just used. A is equal to P times 1 plus r over n raised to the nt power. And let's fill in what we know. Once again, A is the final balance. What's the account worth? And we don't know that, so A is the unknown. But we better then know everything else. P is the principal. How much money did we deposit? $3,500. Good job for you guys for working hard and saving your money. Then it's going to be a 1 plus. And the interest rate here is 4%, but we need to move that decimal. Remember, guys, 2 places to the left. So that decimal is 0.04. I'll warn you guys right now, one of the most common mistakes that I'll see here is people telling me that 4% is 0.4. Nope, that would be 40%. So you really got to be careful about that. Always remember to move that decimal 2 places, not just 1. Okay, then that gets divided by n, the number of times per year, which we said was going to be 4. That's what quarterly means. Close that parenthesis, and now the exponent is the product of n times t. N, once again, is 4, and t, we're not touching our money here, guys, for 5 years. That's the hard part, right? If you have money and you can put it away and not need it, you can do pretty well for yourself. Now, once again, just like in the last problem, A is what we're solving for, and it's already isolated. So all we have to do now, guys, is go to the calculator and type in everything from the right side. We deposited $3,500, and then in parentheses, 1 plus a fraction right now, 0.04 is our annual percentage rate, but we divide that by 4 to get now a quarterly percentage rate. And then, for the exponent right here, we took 4 times per year times 5 years. That means there are 20 quarters at which our bank is going to recalculate our interest. And our answer here, guys, our $3,500 investment became $4,270.67. Okay, 4270.67. Remember, guys, in money problems, we always round to 2 decimal places. So, how did we do there? Not that bad, okay? So in 5 years, we made what? $770 on our $3,500 investment. Now, is that good? Well, I mean, it's not bad. It's all relative. But you might be looking at these 2 problems here side by side and saying, wait a minute, this doesn't seem quite right, because here I did the right thing and I saved my money and I made a little bit here, $700. Here I did the wrong thing. I borrowed money and man, look at how much more I've got to pay back. So the big takeaway right here, guys, is that banks aren't stupid. They're going to take money from you and they're going to say, please put your money in our bank and we're going to pay you a percentage rate of, for example, 4%. But then why would banks do that? They want to take your money so that they can then turn around and loan that money out to somebody who needs to borrow it. And they will charge that second person significantly more than they were paying you for the privilege of holding on to their money. This is how banks make their money, guys. They take it from some people and pay them just a little bit of interest, but then they loan that money out to other people and charge them a really high level of interest. And the difference in those things is where banks make their profit. Now, real quick, just about ready to wrap this up. But I wanted to do one more problem here, guys, just to give you a sneak peek of what's coming at the end of this chapter. So for the account in Part B, everything we just talked about right here, where you're saving $3,500, how long will it take for your principal to double? How long will it take is a question of time. That's what we're looking for here in this problem. So I haven't done that yet, but I start with the exact same formula yet again. A equals P times 1 plus R over N, all raised to the NT power. And if we're looking for time, we better know the value for everything else. Let me actually start right here. The principal is still $3,500. The final amount then, which I'm going to put on the left, I want to be double what I started with. $3,500 doubled is going to be $7,000. That's what I'm hoping to end up with here as my target. Now in parentheses, here we go. 1 plus, nothing else has changed, guys. A 4% APR is 0.04. We divide that by n, which was 4 here, and then we multiply this by a power. That was 4 for n, but we don't know the value of t. So that's what our that's what our equation here looks like. And the question is, how do I solve an equation with the variable located in the exponent? That's actually the skill we're going to learn at the end of chapter 7. We're not there just yet because we haven't introduced the concept of logarithms. So for now, I'm going to teach you guys once more how to cheat. We're going to use our calculator to do this. We're going to graph the left side as just y1, and then we will graph the right side of this equation, everything that we have over here, as y2, and we're going to find out where these two graphs cross. So let me go here. You guys are going to hit your top left button on your calculator, which is y equals. You're going to clear out anything that you have there already, and then we're going to get set here, guys, to start typing in let's see, what am I looking for? To start typing in those two functions right here. I'm going to delete everything that I have and go with that. All right, so on your first line now, you're typing in the left side. We wanted our final balance to be $7,000, and you guys just hit enter, and there you go. Now, you're on the next line, which is Y2, and this is where you type in the right side, 3,500, and then in parentheses, 1 plus, let's put a fraction in there, 0.04 up on top, and down on the bottom was a 4. Right arrow to get out of the parentheses, and we take all that to a power of 4 times t, or we're going to type in 4 times x and hit enter. Now, I've got a feeling, sorry, I did this problem in advance, you guys aren't looking at the exact same graph that I'm looking at. When you hit graph in the upper right-hand corner, you might not see anything. So what I'm going to walk you through here, guys, is how to adjust your viewing window. We'll do this again. So for you guys, I believe that's the F2 key at the top row of your calculator, the second one from the left, and you're going to hit that button right there, and for me, I'm going to go here in Windows Settings, and we should be at a screen that looks roughly like this. And let's talk about the 4 things we might need to change. X minimum. I don't know where you guys are right now, but let's talk about it. X in this model is measuring time, and the lowest time value you can ever deal with is 0. We can't have negative time. So X min should definitely be 0. X maximum, now this one is a guess. We're basically guessing what the answer to this problem here is. And if I thought about this for a minute, let's take a look. We left our money alone for 5 years, and it went from $3,500 up to $4,270. That's a so-so increase, but it definitely didn't double. So it's definitely going to take longer than 5 years in order for this amount to double, and I really have no idea how long. So I just took a shot in the dark right here, guys, and I guessed 20 years. If you're not sure, guess high. It doesn't really hurt you if you guess a number that's too big. Don't worry about X scale at all, guys. You can leave that one alone. Now, Y minimum. Y in this function is measuring the amount of money in your account. And so I would ask you guys, what's the lowest amount of money that you can ever have? Well, 0 would probably be an answer, but in the confines of this problem, you're starting with $3,500, and this problem makes it sound like the amount of money is only going to go up. So in that regard, $3,500 is a pretty good minimum there because we shouldn't ever have less than that. And why maximum? Well, the longer we leave our money in this account, in theory, the more it's going to earn here. Okay, so that's a good thing. But I went ahead and put in 8,000. 7,000 is the target that we're looking for. You just want to put in something a little bit bigger than that so that your graph isn't too crowded. So if you've set your X min, X max, Y min, and Y max to these same numbers that I have right here, when you guys go to the upper right-hand corner and hit graph now, you should get a graph that looks just like this, I hope. All right, so with that in mind, here's our two graphs, and it looks like we guessed right, guys. 20 years was big enough, although not by a ton right there, to see where these two curves cross. So to actually answer the question, we're going to use our calculator now to figure out where that point of intersection is. For you guys, you're going to hit second and then F4, and that gets you to the calculate menu. For me, I've got to go here, and then I've got to go to analyze graph, and then we all want to hit intersect or intersection. And if you've done this right on your TI-84, you guys should just be able to hit enter 3 times in a row. Enter, 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 and that should get you the result. I've got to be just a little bit more creative here. I need a left bound there. I need a right bound here. And there it is. Hopefully you guys are looking in the bottom left-hand corner of your graph, and it's telling you that the point of intersection has an x-coordinate of, just like mine, 17.4152 blah, blah, blah. And in the lower right-hand corner, it should tell you that y is equal to 7,000. We're interested in that x value, which is representing time. So, without any specific directions to the contrary, we're going to round to 2 decimal places. 17.42 is going to be our answer here to this problem, guys. So let's jot that down. T is equal to 17.42 years. So that takes a long time, guys, but for money to double at 4%, yeah, that seems pretty realistic. All right, guys, that is everything I wanted to do with you in a very long section of 7.1. So hopefully by this point, and we've done a lot of stuff here together, you guys are getting a pretty good sense for what exponential growth functions do and what they look like, something like this, and you're able to have some success as you dive into your homework. So give that a go, but let us know when you guys have some trouble there. Good luck, everybody.